So we've looked at Lewis structures, which gives us a good way to represent molecules in 2 dimensions on paper. We'd now like to look at a better way of representing them, and that is with 3-dimensional structures. And by better, I mean a way that is more in accord with reality. The shape of a molecule is determined using a theory which we call valence shell electron pair repulsion theory, or VSEPR theory. There's no need to memorize this, but if we want to simplify it, what it's essentially saying is that the electron pairs that go into making bonds, or the electron pairs that go into lone pairs, repel each other. And we know that anything with like charge, so electrons, will repel one another. So that means that these groups are going to take up as much space as they can to get away from one another. So we have 2 distinct types of what we will call electron pairs or electron pair groups. The first is what we'll call a bonding electron pair or bonding electron pair group. And we get one of those for every atom a central atom is bonded to. And it doesn't matter whether it's a single, a triple, or a double bond. Every atom counts as only one electron pair group. And then we have non-bonding VSEPR electron pairs, and that is for every lone pair of electrons on the atom, and very specifically on the central atom that we are looking at. So let's take a look here at how we would determine these numbers for some typical molecules. So over here I have ammonia. Let me identify the bonding pairs. So nitrogen is the central atom. It's bonded to 3 atoms. The nitrogen also has a non-bonding lone pair. So in summary, there are 3 bonding pairs and 1 non-bonding pair for a total of 4 electron group pairs. How about water? The oxygen is the central atom. It is bonded to 2 atoms, so there are 2 bonding pairs. The oxygen also has 2 lone pairs, so we will call those the non-bonding pairs. So 2 bonding, 2 non-bonding, and just like this molecule over here, we have a total of 4 electron pair groups. And then finally, for formaldehyde, the carbon is the central atom. It is bonded to 3 atoms. Notice that we don't care about the lone pairs on other atoms. And the carbon itself has no lone pairs. So this has 3 bonding pairs and 0 non-bonding pairs for a total of 3 electron pair groups. So I first want to start by looking at these electron pair arrangements. So we can get 3 different arrangements around the central atom, and that just depends on the number of these different electron pairs. First, we can have a central atom bonded to 2 electron pairs. These 2 must be atoms, because by definition, to be a central atom, it must be bonded to 2 atoms. So I don't want you to think of these as lone pairs, even though they look like them. So what we're just showing here is that these electrons are being shared with another atom. So we call this electron pair arrangement a linear arrangement. And the 2 groups are 180 degrees from one another. The next group here is what we will call a trigonal planar arrangement, and that is when a central atom has 3 electron pair groups around it. What are the possibilities? Remember that to be a central atom, you have to have at least 2 atoms bonded to you. So all 3 of these could be atoms, or 2 of these could be bonded to atoms and one of them be a lone pair. So there's 2 possibilities there. And so when we get to shapes, those will each have their own names. However, they will share the trigonal planar arrangement of electron pairs. The electron pairs are approximately or exactly, depending on the molecule, 120 degrees apart in space. I'm not quite sure what this figure means here. This would likely be just a display problem, so please ignore that. The tetrahedral arrangement is what we get when we have a central atom with 4 electron pair groups around it. And the bonding angles there are 109 degrees apart in space. You'll notice that this is the first of the groups that we've seen which is truly three-dimensional in structure. And although it's going to usually be represented on paper in 2 dimensions, in fact it's always going to be represented in 2 dimensions, although we will try to simulate 3 dimensions later on, we must remember that these groups are all actually 3-dimensional. And that's why even if we draw these like a cross, they're not going to be 90-degree angles, but instead much closer to 109 degrees, or more specifically 109.5. So how many possibilities can we get here? Well, the central atom could be bonded to 4 different atoms. It could be bonded to 3 different atoms and have a lone pair. Or it could be bonded to 2 atoms and have 2 lone pairs. Again, a central atom must have at least 2 atoms bonded to it. So there's no 1 atom and 3 lone pairs. That's not possible. So what we're going to do now is generalize the electron pair arrangements into molecular geometries, also called shapes. And they're going to be based on those Vesper pair arrangements. In this class, we consider only 6 different possibilities, and that is what we are limited to when we are following the octet rule. And we've committed to following the octet rule in this class, and therefore those are the 6 geometries we will get. So we determine these by counting 2 numbers, the number of bonded electron pair groups and the number of non-bonded electron pair groups on the central atom. If a molecule has more than 1 central atom, then each of those central atoms gets its own molecular geometries. For right now, let's only focus on cases where there is only 1 central atom. And in several of these cases, the molecular geometry's name is the same as the valence shell electron pair repulsion name. That's going to be the case whenever the molecule is only going to have bonded groups and no non-bonding groups. So we'll start off with what could be argued as the simplest, and that is the linear shape or linear molecular geometry. And that's what we get when we have a central atom bonded to 2 other atoms. There are no lone pairs. Now I know some people will say, oh, but Professor Katroulis, there's a lone pair right there. But remember, we're only looking at the central atom, and it has no lone pairs. So the carbon has an atom on this side, an atom on this side, and a 180-degree angle separating them. That's the bond angle. There's no other way to have 2 electron pair groups arranged. So now we look at the ones with 3 electron pair groups arranged about the central atom. So if our central atom is bonded to 3 other atoms and has no lone pairs, it's said to have a trigonal planar shape. And with trigonal planar shapes, we have 120-degree angles approximately. Since these 3 atoms are not all the same, that would only be approximate, but 120 degrees is a good enough guess for what we need to do here. And so here we are showing this molecule. It's called planar because if we were to build this model and put it on a table, it would lie flat, as if it's on a plane. What if instead we have a central atom bonded to 2 atoms, but we have a lone pair here instead of an atom? That's what we get when we have an angular type molecule, like we see here. So sulfur dioxide, which we just drew the Lewis structure for a moment ago, is a typical example of such a molecule. You'll notice that we do not typically show the lone pairs in our three-dimensional shapes over here. And since we pretend not to see this, the only thing that we can focus on is the bent shape here. I should note that even though I have the term angular here, the word bent is also commonly used for these shapes. Now we move to the molecules which have 4 electron pair groups about the central atom. These are called tetrahedral geometries. So we have here carbon bonded to 4 hydrogen. This is called methane. We saw it a moment ago. And you will notice that the molecule as drawn here looks completely flat, and it looks like these angles are 90 degrees. And that's often how we draw it on paper. However, I think you can clearly see here that this angle is greater than 90 degrees. This is 109.5 degrees. And that's because it's not a flat molecule. It's a three-dimensional molecule. So this is a tetrahedral shape or molecular geometry. Here we have ammonia, and the nitrogen is bonded to 3 atoms, so it's 3 bonding groups, and 1 non-bonding group, a lone pair. This is called trigonal pyramid or trigonal pyramidal. So adding an AL there is also a typical part of the name. There is a lone pair here. It takes up quite a bit of space, and it kind of pushes these hydrogens down. The bond angle is expected to be, again, about 109.5. In reality, it's a little bit less, but we're not going to worry about that. 109 will be fine for us. And then finally, what we get when we have 2 bonded groups here and 2 lone pair groups, like we see there, so still a total of 4 groups, is what is called another angular or bent shaped. And these are also sometimes called V-shaped because they look like an upside down letter V. So we already saw another shape that had that exact same name. But the difference here is because there are 4 groups on this atom, 2 lone pairs, 2 atoms, the bond angles are smaller than the previous shape with this name. These bond angles are expected to be close to 109 degrees. In reality, it's actually closer to 104, but we don't need to memorize that. We're just going to say 109 degrees. So let's make a summary here. So if we are trying to figure out the shape geometry of a molecule, you have to begin with a Lewis structure. There's really no other way to do this because you need to see if there's lone pairs on the central atom or not. You count up the number of bonding electron pairs and the number of non-bonding electron pairs, and then you determine a geometry from that. Now this actually comes from a different textbook, and it's essentially the same as what we have in our book with one major exception, and that is they prefer the term bent in your textbook to angular, although those terms are synonymous with each other. You can change one for the other. So whenever we have a total of 4 electron pair groups, which could be 4 bonding, 3 bonding plus 1 non-bonding, or 2 bonding plus 2 non-bonding, these are all going to have a tetrahedral type geometry with 109 degree angles, and these being the specific names. When we had 3 electron pair groups, meaning either 3 bonding or 2 bonding and 1 non-bonding, adding up to 3 there, the bond angles are about 120 degrees. They have a trigonal planar electron pair geometry. But these are the actual molecular geometries that we're going to focus on. So here we have trigonal planar, and here we have angular, which again is usually called bent. Your textbook leaves this one out, but I would call this, again, bent in most circumstances. And then finally, if the central atom is bonded to 2 other atoms and has no lone pair, that's the only possibility here. We have a linear electron-pair geometry, which is also a linear molecular geometry. That's the only way to get that. So here is a good summary of all the different possibilities that we could get. So you'll want to be sure to learn these and apply these to molecules that you see in the textbook. I'm now going to move on to our final topic, and that is the topic of polarity. So if two atoms are covalently bonded to each other and they have very different electronegativity values, we say that that bond is polar covalent. You'll notice right now I am focusing only on bonds. By substantially different, I mean that the electronegativity difference between the atoms is 0.5 or greater. And typically it must be less than 2. Anything greater than 2 would be an ionic bond. So the electrons are not shared equally. They are pulled towards the more electronegative atom. So we can almost think of the more electronegative atom as like an electron vacuum cleaner. It is sucking the electrons towards it. And those electrons spend more time towards that atom than they normally would towards the other atom. If the electronegativities are the same or very close, the bond is described as nonpolar covalent. And by close, what we mean is a difference of 0.4 or less. We can typically show the polarity by drawing special arrows which point towards the negative side of the molecule. We actually usually start by doing this bond by bond, and then we see how those arrows add up. We're not going to go too much into the details of drawing these arrows, but what we are going to try to do here is recognize when molecules are probably polar and when they aren't. So here's an example of a polar covalent bond. Here we've got 2 electrons standing for the bond, but we could have just as easily had a straight line there. Fluorine is much more electronegative than hydrogen. If you recall, fluorine has an electronegativity of 4.0. Hydrogen is 2.1. This is the most extreme example we can have of a covalent bond. If the electronegativities were any different, we would start considering this an ionic bond. So 1.9 is our absolute maximum in difference. So this means that the electrons are being pulled much more towards the fluorine than they are towards the hydrogen, and the sharing is extremely unequal. What about if we have 2 fluorines? Well, this one has an electronegativity of 4. This one has an electronegativity of 4. So the difference between them is 0. So even though they're both extremely electronegative, they both are pulling the electrons towards themselves with the same vigor, which means that ultimately the electrons are shared perfectly between those 2 atoms. Now, what happens when we start adding more than 2 atoms to the molecule? Let's look at this case here, where we have carbon dioxide. On the one hand, there's a fairly substantial difference in electronegativity between carbon and oxygen. Oxygen has 3.5 as its electronegativity, and carbon has an electronegativity of 2.5. That's a difference of 1. So that means this is definitely a polar covalent bond. So these electrons are definitely being pulled towards the oxygen. However, we have the exact same situation on the right side, with these electrons being pulled quite vigorously towards this oxygen. And so it's kind of like a game of tug of war, where we imagine the carbon atom being in the middle and the electrons being yanked in either direction. Whenever we see this kind of a situation, where we have a central atom bonded to exactly the same kinds of atoms, it is not going to be polar. The polarity will cancel out. Now let me expand on that. If there were a lone pair on the central atom, this would not be the case, because then the molecule would have been bent. The electrons would have been being pulled down, and there would be nothing to push back, pulling up. So this is something that you'll want to make a note of. If you only have one central atom, and the central atom has one or two lone pairs on it, any lone pairs, it will almost certainly be polar. As for nonpolar, you get them when you have one central atom bonded to all exactly the same atoms, or you have bonds which are nonpolar. Here's another fairly extreme example: boron trifluoride. You might notice that this is a bit of an odd molecule because the boron does not have an octet. We're not going to talk about this much because boron is a rather unhappy element, and it's kind of typical for boron not to satisfy the octet rule. You might say, well, why doesn't it borrow one of fluorine's lone pairs? But remember, we said fluorine doesn't share. It's very greedy about its electrons, and that's important in this case. So what we see here is it's like a game of tug-of-war with three people. And so if we assume that each of these people are equally strong, so they're just like fluorines, and we assume that this rope is the same length on all sides, and they all pull, this isn't going anywhere. It won't go up, left, down, and right down. It can't, because equal force is being pulled on them. So even though these bonds are polar bonds, they cancel out, and this molecule would be nonpolar. Again, if for some reason there were a lone pair here, that would not be the case. The shape would no longer be trigonal planar, it would be trigonal pyramidal, and the electrons would go towards the three fluorines in that kind of a situation. However, there is no lone pair on this boron. Let's change things a bit. What if one of those groups were different? So instead of three fluorines, what if two of those were fluorine and another one was hydrogen? So for example, let's say these are still our fluorines, but let's say that this person is pulling with the strength of a hydrogen. They're much weaker, so they're sharing electrons fairly equally, they're not pulling as hard. So what does that mean? It means that as these people pull, you'll notice that this central atom, or this ball, would suddenly go off this way. Just think about that. They're pulling, pulling. This would suddenly take off that way. And so we would say that this molecule is polar, and electrons are being pulled over this way, so to speak. So molecules that are polar tend to attract one another. And we need energy in order to separate them, because attractions always require energy to break. If molecules are nonpolar, which is the same thing as saying they do not have a dipole moment, they don't have one of those arrows going in a particular direction, those kinds of molecules do not have as much attraction for one another, and they're going to be easier to separate. And so what this is going to tell us is that there are differences between the boiling points and the melting points. Molecules that are very attracted to each other happen to usually have high boiling points, whereas molecules which are not attracted to each other or have minimal attractions tend to have lower boiling points. This is a subject we'll look at in much greater depth in the next chapter. Water is the classic example of a polar molecule. It's very important to know that. It is polar because oxygen is electronegative. The hydrogens are much less electronegative, so where are the electrons going? They're being pulled this way and this way. There's nothing to push back from this side because there's lone pairs here. So what that means is that this side of the molecule is negative. And we use this symbol here to call this a partial negative charge. So it's not a full negative charge like we do with ionic compounds, but it is negatively on that section. The hydrogens, on the other hand, because they are less electronegative, are deprived of the electrons, and so this side is positive. So the term polar means like a magnet. There's a negative side and a positive side, and we call those poles. just like we do with the Earth when we have a north pole and a south pole. That's related again to magnets. So you'll see here that these molecules tend to like to line up with the negative side close to the positive side. Negative close to the positive, negative close to the positive. That's generally true throughout here. So these molecules will adopt this arrangement. Because they are attracted to one another, we have to put quite a bit of energy in to separate them. And it is incredibly unusual for a molecule with this low a mass. As we'll see in Chapter 5, the mass of this will be about 18 grams per mole. That's a small number. Or we would say this molecule has a mass of 18 AMUs. Very, very low mass, but still a very high boiling point because of this intense attraction. On the other hand, look at liquid nitrogen. Nitrogen is totally nonpolar. There are two atoms, nitrogen. Since they are identical, they have to share the electrons equally. There is no positive side, no negative side, so no reason that one nitrogen molecule would want to be attracted to another one. We will talk about a very weak type of an attraction called the London forces in Chapter 4, but they are extremely weak. And what does that mean? It means very little energy is required to separate them. And in fact, if you pour this into a container that's at room temperature, so say for example this glass was at room temperature, or you even poured it on the floor, it would almost instantly become a gas. That would be enough energy to separate these molecules from one another. And to make a point of this, let's look at some polar molecules. Hydrogen fluoride is about the most polar molecule that we can get, and its boiling point is about 20 degrees. That might seem kind of low, but compared to the values here for nonpolar molecules, that's much higher. Water has a very high boiling point owing to the fact that there are two hydrogen atoms there and two lone pairs on the oxygen, so that better balances out these charges. Again, this is something we'll see more in Chapter 4. And ammonia, even with a boiling point of -33, is substantially higher than for the nonpolar molecules here. So, as I said, we will illuminate this topic a little bit more in the next chapter when we talk about intermolecular forces. However, this finishes off Chapter 3. I'd like to thank you for watching and urge you to continue on to the next chapter. Thank you.